Hello and welcome back to STEM Online Academy. All right, today we are going to look at why this tangent line creates the smallest possible triangle. If you look at my picture here, okay, pretty interesting problem. All right, so most students are going to hear this problem and immediately think, hmm, okay, yeah, it looks like we need to find the tangent line, find the intercepts, build the area, differentiate. But that is the exact trap to this problem. Okay, there is no actual minimum. Okay, there is no actual minimum to this problem. Okay, if you read the problem here, I'm not going to go all through it. Um, Part of the main bulk, main meat of the problem here is this: find the for which the triangle has minimum area. The problem is though this problem has there is no actual minimum. Okay, so the area can get, if you look at my drawing, the area can get smaller and smaller, but it's never smallest for any positive value of a. Okay, I'm going to explain why. Okay, explaining in words is more, I think, is more important than going through all the algebraic steps. The algebraic steps is just the basic technique you should be able to do by now. All right, so let's look at this. Right, so that is exactly the kind of this is exactly the type of calculus exam trap that catches students off guard, right? Because all of you have been so used to computing before actually understanding the geometry of the problem or the reasoning of the problem. Okay, so let's look at the diagram, right, to this problem. So we're given a curve, as it says in the question, root x, tangent line at point coordinates a common root a, intersects the coordinate axis, and forms a triangle. Find the value of a strictly greater than 0 where there's minimum area. So that's part A, and then there's part B, then determine the minimum area. So I drew the diagram, okay? So let's look at it, right? So if you look at the problem, right? So we're looking at this curve here, y equals root x. Okay, so y equals root x, that yellow curve here. Okay. And what you're going to notice, yeah, square root of x, that means that square root of x, that means that this thing has to be positive, right? If you have square root of x, the domain of all x numbers have to be greater than 0. Otherwise, it wouldn't make sense. Okay. So at a point on the curve, we draw a tangent line. Okay. Now, be careful how you're drawing it. It's going to be going from left to right here. So it intersects the y-axis and then comes down to the x-axis. Okay. Right? And the reason why it's drawn that way is because we're trying to form a triangle. Okay, so the tangent line intersects both the coordinate axes. Okay, so let me just get my marker here. Just hang on a moment. This coordinate axis, the y-axis, and this coordinate axis. I'm pointing here, the green arrow, the x-axis. Okay, so it intersects both coordinate axes. That's important to know. Note, right? So together with these axes, he forms a triangle, right? Because if you drew the line, my white line here is my tangent line, right? Okay, go like that, intersecting the yellow curve at exactly a comma root a, the coordinates. That's the tangency point. I drew the line like this because then I can form my triangle by creating, let's carefully here, going to the left now, right? That's how I knew how to draw my line, okay? So together with the axes forms a triangle. So the question you have to ask in this problem, okay, the question you need to ask yourselves is which point gives the triangle the minimum area? Which point? Really, which point is it? So, because if you don't ask that, you're just going to go through the routine motions of algorithmically saying to yourself, okay, determine the slope, determine like getting the first derivative, substitute the coordinates, and get a tangent line. No, that would be wrong, downright wrong. Okay, I'm sick and tired of schools teaching mathematics in a very algorithmic way. It's not helping you for midterms. It's not helping you for exams, and it's not helping you in your further careers. Okay? You need to be able to think fluidly. Okay, so so the specific problem is we want to find the tangent line that cuts off the smallest triangle from the axes. Again, we want to find the tangent line. Okay, so I've highlighted in red here my tangent line. Right, my tangent line. Find the tangent line that cuts off the smallest triangle from the axis. Okay, and we're about to do that. However, I want to explain. I want to talk a bit about me. For those of you who are new to the channel, uh, a little bit about myself. Right, I'm Jason. I'm Jason Masterakos, the founder and president of STEM Online Academy. So my short story connection and how you can maybe a lot of you can relate to it. I don't know. I used to get stuck on problems like these. Right, I wasn't always good at math. When I was in grade 7 and 8, actually, I struggled. Yeah, I struggled. Not because I didn't know, like, the procedures. I knew the formulas, right? The problems were that I would start computing before asking. I would start calculating things before questioning and analyzing the problem. Most of you are just calculating without analyzing the problem. Okay, if you do that, you're going to end up in big trouble, especially in university. Okay, uh, so that was the main problem. So you have to ask yourself, what is the geometry actually doing in a problem like this? This is analytic geometry. Yes, it's calculus, but the prerequisite for this problem requires analytic geometry. Okay, so what is the geometry actually doing? And what it came down to is there were these two teachers that I had that changed my life forever, practically. Okay, really, they did, uh, and landed the career that I want. Well, I don't know if it's a career, but something that I love doing. Right. Once they showed me how to do mathematics, the two teachers that did that changed this for me, and they taught me to break hard problems, any hard problem, into a system that works for you. That's first off what you have to get down in your heads. You need a system, but you need a system for anything, right? You need a system to do anything right. Okay. Now, here's my system that I've come down with, especially with a problem like this, which is very geometric, or it could be a physical problem, doesn't matter. You want to step one, right? So let me just put here. First, you want to be able, right, to visualize, let's draw the diagram. Okay, so you want to visualize. Okay, so visualize. That's the first thing you want to do. Step one. Step two is you want to model. Step three, okay, you want to be able to execute your strategy from the model. And then step four, you want to verify. Okay, that's my technique. I call it my systems technique, for those of you who don't know. And that system helped me go from struggling in math to earning a double honors degree in mathematics and physics at university. And I finished with a 3.9 GPA out of 4, which is very high, by the way. It's almost perfect. Okay, so let's use that system here. Okay, let's use that system to try and make sense out of it through language, through communication. Okay. So again, let's look at the picture. We want to visualize that tangent line. Okay. And we want to draw our tangent line such that it hits exactly 1 point on y equals root x, right? And that it hits at least one of the hits both coordinate axes, the x and the y axes. Okay. So again here, this point here, this axis here, and this axis here have been intersected. Okay. All right. So that's what we want to do. We just want to visualize. Visualize the tangent line. And then for the square root curve, y equals root x, okay, the tangent line at a positive point is going to slope up. Okay, so for the square root, right, it's the square root curve. So if you look at the square root curve, the yellow curve here, okay, the tangent line will be at a positive point, right? That is sloping upwards. Okay. If you can't visualize that, try and think this way, right? Okay, sloping upwards. This is a positive slope. Okay, that green line there. I'm just, it's not, you don't need it, but just to visualize for you. If you extend that tangent line, right, it cuts off on the y-axis above the origin, right? So it's going to extend. So if you look carefully, right, it's going to extend, right? So over here. So yeah, this was the initial tangent line that I was talking about, the white line. Don't get confused. That white line here, right? This line here intersecting the blue axis, that's my tangent line. I just put that green line there. It looks like a tangent line too. It's just trying to show that there's a positive slope for y equals root x if you were to analytically try to visualize the slope or the derivative. Okay, so we have our tangent line, the white line there. Now, if you extend the tangent line, it cuts on the y-axis, right? Y-axis above the origin. Yes, it needs to be above the origin. Here's my origin, point O. There's my point O there. I like to write my point O's better. Point O. Okay, it's above the origin. But it cuts the x-axis to the left of the origin. Yes, what I mean by that is cuts the left axis like this, right? So the triangle, as you can see, right, is formed using positive y-intercept, negative x-intercept. Okay, one's positive, right? Positive y-intercept is here. That's my y-intercept, my x-intercept, negative x-intercept over here. Okay? And the origin. That is the picture. So the triangle exists, but it's just sitting partially on the negative side of the x-axis. Now, we've done visualize. Okay, we've done the visualize part. We've done the visualize. I'm going to underline when we finish something. Now we're going to the model. Okay, so let's do that. Let's look at the model. So now we model the area. All right. So what do I mean by that? We may need another page here. Okay, let's go to another page. So we model the area. The base of the area of the triangle, sorry, the base of the triangle, base of the triangle comes from how far the tangent line hits the x-axis. I think you can see that here, right? Right. So the base of the triangle comes from how far, right? How far, right? How far left the tangent hits the x-axis, right? So this here, that's what I was talking about. Okay, basis of the x-axis. Now, the height comes from how high the tangent hits the y-axis, right? Think about it. Okay, from the y-axis. And when you compute those intercepts, something is going to happen. So you need to compute those intercepts. That's the process, the reasoning process for this. So something interesting is going to happen. As the tangent, so I want you to visualize on the drawing here. You may need to sort of move it around in your mind, right? So as the tangent point moves closer, think about it. As the tangent point moves closer and closer to the origin, both base and height will start to shrink. Okay? I think that's obvious, right? As the tangent point moves closer and closer and closer to point O, right? Point O at the bottom here, right? So let's not get confused, point O. Both base and height will shrink. Okay, so the triangle also shrinks. And that will give us the minimum area that we're looking for and how to analyze this problem. You see how I'm analyzing it? I haven't even gone to doing any like equations, right? Because mathematics is about reasoning, not formulas. Okay. So both base and height will shrink. So the triangle will also shrink. the area is not minimized at some beautiful interior points or whatever you want to call them, right? It just keeps getting smaller and smaller as the tangent point moves towards zero. Okay. So we've done visualize model. Now we need to execute. So execute. Now execute, we're going to execute, by me execute, applying the reasoning even further. Okay. So for every point, positive value of A, okay, so I want you to think about that, right? So for every positive value of A, so let's go over here. So for every, I'm going to write this down. So for every positive, right? So for every positive value A, so for every A greater than zero, the triangle, right? So the triangle has positive area. Can't have negative area. No. So it has to have so yeah, so for every positive value A, the triangle has positive area. Positive area. We call this A for area. Okay. So for area, capital A will be strictly greater than zero, which is positive area. Okay. Now, if you choose a smaller positive value, I want you to think about this. If you choose a smaller positive value of A closer to zero, right? So closer to zero, right? Uh, the triangle is going to become smaller again, right? So let's go back to our visualization, right? So if you choose an even smaller positive value, the triangle will become even smaller again. I think you could visually and logically make sense out of that. Okay. All right. So what comes down out of this, the implication of this is that no matter what positive value you choose, I can always choose a smaller positive value and get a smaller triangle. In other words, it's almost like getting uh, what's the word mathematical to be precise here, uh, a greater lower bound, you can say. I don't know if any of you've taken analysis. That's a part of calculus. You do real calculus. But in reality, what I'm saying here is that no matter what value, so I'm just going to put it here. So no matter, so it's the implication. So no matter what positive values, it's okay if you don't know what a greater or lower bound is. That's fine. Positive. It's just mathematical precision in terms of how I'm explaining it. I just wanted to be very precise. So no matter what positive value you choose, I can always choose a smaller smaller positive value and get a smaller triangle. Yeah, a smaller triangle and get a smaller triangle. I'm writing this down because it's very important. It's the only way you're going to understand the reasoning. Okay. In other words, I'm saying that there's a greater lower bound, right? Lies a G, an infimum. Yeah, yeah, infimum. Some sort of infimum in terms of the area. Okay. So there's an infimum of the area. It's okay, you don't understand that. For those of you who aren't really deep into math, for those of you who are, you know what I'm talking about. Okay, so that means that there's no actual smallest triangle, and there is only some sort of limiting area, So the area is bounded. The area is going to approach zero, actually, right? So our area, another thing too, our area A will approach zero because we're trying to we're trying to minimize the triangle, right? So it has to approach zero. So the area approaches zero as the tangent point, right? As the tangent. I'll just put here, yeah, as the tangent point. Okay, so as a tangent point, let me think here. Tangent point approaches the origin, approaches the origin. Okay, we discussed that earlier. Now, since A must be positive, okay, so since A must be positive, little a has to be strictly greater than 0, the tangent point will never reach 0. So the tangent point will never reach 0. If you have any questions, leave it in the chat. Never reach 0. Reach 0. Reach 0. Okay? So the minimum is not going to be attained, right? So you're not going to find a minimum, right? This implies, this is going to imply, let's think about this, how I'm writing this. This will imply that the minimum is not attained. It's not attained. Okay? I hope that is making sense. Again, if you question any of this, uh, take out a pen and paper, try the problem yourself, go through the reasoning. If you have any disputes, you can always ask in the chat. Okay? I love doing problems like these. These are hard. Yes. All right. So now we've done the execute part. We're going to look at the verify part. Okay, that's the last step. So verify. We're going to do that. Just did this, and we have another page here. Verify. Okay, looking at verify now. The verify phase. Okay. Now, when we verify, we want to verify the conclusion, right? As mathematicians, we have to verify what we're talking about. Otherwise, we're not mathematicians. So the problem asks for a value of a greater than 0. Remember, that's what the problem's asking for, a greater than 0. And the value of a greater than 0 for which the triangle has minimum area. Okay. So we know that gives us minimum area when a greater than 0. So, but every positive value, I want you to get it through your heads, guys. Every positive value can be beaten actually by choosing a even smaller positive value. Right? So some sort of a infimum, you can say, right? So therefore, no positive. If you think about it, no positive a will give you a true minimum. No positive a, because I can always find an even smaller positive value, right? So my bound, my lower bound, will not allow me to find no positive a value that will give me a minimum. Does that make sense? Okay. So the minimum of the I want to say minimum. What was the? Let me think. Just give me a moment to think. Yes, the infimum. So the infimum, right? The infimum of the area is going to be 0. Okay, so I'm just going to put here. Therefore, the infimum. Right? Therefore, don't worry if you haven't learned the definition of what infimum is. I think me explaining it sort of gives you an understanding of what it is. The infimum of A is going to be 0. Okay, you can't find you always get a smaller positive value. Okay, but this minimum at the same time doesn't exist, right? You have to think about it. The minimum doesn't exist. So there's that distinction matters. Okay, you have to make a distinction between the minimum non-existing and not being always being beaten down by finding a smaller positive value of a. So when it comes to this, right, just want to let you know, yeah, we're pretty much done this problem. Okay. So I just want you to take away from this problem here that uh, on a hard exam, this is where students would lose marks. Okay, these types of problems. Okay, uh, they're not easy, trust me. But you don't need to be some sort of prodigy to do them. You just need a system. Okay, so as I was saying, on a hard exam, this is where a lot of you will lose marks. Um, you guys will find an expression. You'll force a derivative right when you see this because you're thinking of tangent lines. The thing is, you just go through the process, the motions of doing, oh, y equals mx plus b. Oh, I need to find m. Oh, they gave me the coordinates. Oh, to get m, I get the first derivative. No, 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 no. So that's where you're going to lose your marks. Okay. So you would, as I said, you would actually find an expression, you'd force a derivative, and you'd assume a minimum exists because the problem says look for a minimum. Just because the problem says something exists doesn't mean necessarily. You need to analyze the problem to make sure that they're not tricking you. It's a trap. Okay. So calculus is not just computation. I want you to get that. Even though the name, yes, the root calc can be confusing for a lot of you. Oh, thinking, oh, I'm just calculating things. No, not even close. You have to verify everything. You have to verify in this case the minimum is actually attained. And it's not here. We've proven that it's not because there's an infima of A. Infima of the area is 0. So what's the main takeaway from a problem like this? What's the point? How does this help you and why should you care? Well, yes, there is no value of A greater than 0 that minimizes a triangle, right? So there is no value, right? So I'm just going to say here, there is, there doesn't, this by the way means doesn't exist for you know the nomenclature I'm lazy to write does not exist, there doesn't exist. There does not exist a value of A. There's a value of A greater than 0. A greater than 0 such that which will minimize the triangle's area. That will minimize the triangles area. Okay. The triangle area actually can be made arbitrarily small, okay, just by moving the tangent point closer and closer, as I said in the diagram. As the tangent point moves closer and closer to the origin, that's how we approach minimization. But because the point must stay in the domain, remember the point has to stay in the domain x greater than 0. Why? Because y equals root x only takes all positive values of x, nothing else. And that is the entire trap. Okay. All right. So if you got stuck here, this doesn't mean that you're bad at calculus. A lot of people get stuck on this and they're doing very well in calculus in maybe their calculus course. Or that's what it is, the perception is. It means the problem was designed to test, right? This problem was designed to test whether you can verify or not verify the existence of a minimum in this problem. Okay. And the verification comes from doing systematic, step-by-step, systems-based approach. Okay. You want to remember, visualize, model, execute, and verify. Okay. This is exactly what I teach. If you understand examples but freeze when exams turn tangent lines into optimization traps, I want you to download my free guide. It's for free. You can get it on my in the link below, my YouTube video. Be free. So I want you to download it. It's very important. Okay. If there's nothing else that you do today, at least download the like PDF. And if you want help applying the system to your, midterm or your final or to prep throughout an entire course, my coaching link will be in the description below for the YouTube channel. a YouTube video. I want you to comment triangle if you want more hard calculus optimization problems. I always like to get feedback from my audience. Tell me where I'm going. And don't forget to like and subscribe. Please like and subscribe. It helps us move up, move up on the algorithm. And there's going to be plenty of more interesting problems coming up next week. Probably going to do 3 if possible. I might try to do 3 videos. I do 2 minutes. Always I do 2, but it's going to be trying to do 3 next week. All right, guys. Have a great day. Bye-bye.